Hi, in the last video we presented another convergence result without proving it. And in this video, I'm going to use the second mean value theorem to prove this result. Let's recall the result. The result states that if f is an integrable 2-pi periodic function on the closed interval -pi to pi, and we suppose that f is piecewise continuous and increasing near the point x which lies inside the interval -pi to pi, then the Fourier series converges to the average between fx plus and fx minus. Fx plus is the right-hand limit of f, while the fx minus is the left-hand limit. So, how can we prove this? Well, for simplicity, we will just take x equal to 0. Using the evenness of d and z, we can write the Fourier series at 0 as the integral from -pi to pi of fz d and z dz, which is equal to the integral from 0 to pi of fz plus f minus z times d and z dz. Also, remember that the integral from -pi to pi of d and z is equal to 1, so by the evenness, we know that the integral from 0 to pi of d and z is equal to 1/2. And also, we know that fx plus fx minus over 2 is equal to the integral from 0 to pi of fx plus fx minus times d and z. So, the difference between s and f0 and the average between fx plus and fx minus is equal to the expression here. So, it is equivalent to show that the integral from 0 to pi of fz minus fx plus times d and z tends to 0, and the integral from 0 to pi of f minus z minus fx minus times d and z tends to 0 as n tends to infinity. I will just prove the first statement here, and the second statement I will leave it as an exercise because the argument is essentially the same. We use the similar skill as before. We will divide our integral into two parts. The first integral is the integral from 0 to h for some small h greater than 0, and another part is the integral from h to pi. Let's first consider the first part. Well, the first part is the integral from 0 to h of fz minus f0 plus times sine n plus 2z over sine z over 2 dz. Well, if we subtract sine n 1/2 z over z over 2 and plus this expression, then we will get the second line here. After that, we can apply the L'Hopital's rule to prove that 1 over sine z over 2 minus 1 over z over 2 will tend to 0 as z tends to 0. So it means that from the definition, for all epsilon greater than 0, there exists an h1 greater than 0 such that the absolute value of 1 over z over 2 minus 1 over z over 2 is smaller than epsilon, as the absolute value of z is smaller than h, and this such h is smaller than pi. So, using this fact, we know that this expression here is smaller than or equal to the integral from 0 to h times 2m times epsilon over 8m pi. Well, here m is the maximum of fz in the interval -pi to pi, and this expression here is a sine function, and therefore it is smaller than or equal to 1. On the other hand, we know that this epsilon here is arbitrary, so we can simply replace our epsilon by epsilon over 8m pi, and therefore if we compute such integral, we know that it is equal to epsilon over 2 times h1 over pi. And as h1 is smaller than pi, we know that it is strictly smaller than 1, and therefore this expression is smaller than epsilon over 4. The second part is the integral from 0 to h of fz minus f0 plus times sine n plus 1/2 z over 2. And using the second mean value theorem, we know that there exists a k inside the open interval 0 to h such that it is equal to fh minus fx plus times the integral from k to h of sine n plus 1/2 z over 2 of dz, and plus f0 minus f0 plus times the integral from 0 to k of sine n plus 1/2 z over 2 dz. In the case of h tends to 0, we know that k tends to 0, therefore the second integral here will obviously tend to 0 as k tends to 0. And that means for all epsilon greater than 0, there exists an h2 such that f0 minus f0 plus times the integral from 0 to k of sine n 1/2 z over 2 will be smaller than epsilon, as the absolute value of h is smaller than h2. And we claim that the first integral will also be tends to 0 as h tends to 0. We consider the absolute value of the integral from k to h of sine n plus 1/2 z over 2 dz. Using the transformation t equal to n plus 1/2 z, we know that this expression can be transformed into this line. We then divide our integral into from 0 to n plus 1/2 h and from 0 to n plus 1/2 k, and apply the triangle inequality, we will get this line. And we are going to claim that big fx equal to the integral from 0 to x of sine t over t is a bounded function on the interval 0 to infinity. In fact, it suffices to prove that the integral from 0 to infinity of sine t over t is finite. And I will leave it as an exercise to figure out why it implies that big F here is bounded.